Welcome to Chemistry 111. Hopefully you have gotten everything you knew about Lewis structures and all about Vesper theory, because that will still be on the upcoming test 3. However, this last chapter is a completely different piece in that we'll be moving away from Lewis structures and now more into the math and kind of the chemistry side of things. Rather than looking at individual molecules or compounds, we'll be looking at how these compounds interact. So we'll start with some basic chemical reactions and aqueous solutions. This chapter in itself is probably one of the easier and shorter chapters available. However, the last part, when it comes to aqueous solutions, can be a bit tricky. So starting right off, looking at the idea of a chemical reaction. Hopefully, if you had it in high school chemistry at all, this part is rather familiar to you. If not, we will go through the basics of diagramming a reaction. Chemical reaction is the conversion of a reactant into a product. Now, a reactant is just artificially defined as what is our starting components, the things that do the reaction. Our products are whatever gets formed in the reaction. Now, typically, we're going to write them left to right. However, that is just out of, it's not important that it be written right to left, left to right. We follow the arrow. The arrow points up. If you have to take chemistry 2 at all, we will get more into what is called a reversible reaction, and that you often have an arrow that points left to right, followed by an arrow that points right to left, saying that depending on which way you look at this, you could have reactant could be product or product could be reactant. Right now, I'm showing the act of rusting, the oxidation of iron to form magnetite. Well, no, sorry, not magnetite, but hematite, which is the basic structure for rust. However, it is possible to reduce rust back into standard iron. The hematite is the same thing as a mineral you can also dig out of the ground. You can dig that out of the ground and throw that in a blast furnace and convert it all the way back to into iron, where it can be then formed into whatever you need to do. So right now I'm showing the reaction going iron plus oxygen goes to iron oxide, iron 3 oxide, but I could draw it the other way around where iron 3 oxide goes to iron and oxygen. Now, despite this conversion, you should notice the total amount of iron on left and right are the same, and the total amounts of oxygen on left and right are the same. We have 4 atoms of iron goes to 2 atoms of iron oxide, but the iron oxide has 2 atoms of iron per compound. So 2 times 2 is 4. 3 molecules of diatomic oxygen means 6 oxygen atoms. 2 times 3 iron oxides, 6 oxygen atoms. So on left and right, the total atoms of each type should be balanced. So how can we tell reactions take place? Because we can't see these molecules usually. We can't necessarily see that a molecule has changed the atomic rearrangement. Now, how can we observe a reaction take place? Sometimes it's a change in color. You should know, if you ever have some iron, it becomes red and flaky, it's probably been converted into the rust. A production of light, so that's sometimes a result. Formation of a solid, so I pour 2 liquids together and we get a solid. That's one type of reaction we'll talk about a little bit later. Formation of a gas, I pour 2 liquids together, or a liquid and a solid, and something bubbles off. Another good one is the absorption or release of heat. So does pour two liquids together, does it get hotter? Does it get colder? All these could be a hint that some sort of reaction is taking place. Now, when we balance a chemical reaction, we want everything to be the same on both sides, the same number of atoms. Now, we cannot change these subscripts on a chemical compound, because if I change that Fe2O3 to anything else, like FeO or Fe3O4, ought to have a completely different compound. We're not allowed to change the subscripts of a given reaction, but we can change the quantities of given molecules. So we're going to use what we call coefficients. Coefficients are typically going to be integers we use to balance a chemical equation. Now, on occasion, we'll use halves and like non-integer values, but that's only for very special definitions. Typically, we are going to want whole number integer values on our balancing. We're going to try to keep that. That's how we're going to answer, at least for the test. So looking at the reaction, this is the thermite reaction. Aluminum plus iron oxide goes to iron and aluminum oxide. And what is not shown here is a buttload of heat. So much heat, it will cut through steel. And you'll have iron slag for at least a brief moment. Putting that on, you could, I mean, that's how they kind of welded like railroad ties together. You could put that on and kind of seal the thing. So we see on here, there's one aluminum molecule on the left, two on the right. Two iron molecules on the left, one on the right. Three oxygens on the left, three oxygens on the right. So the oxygen is good. So the easiest thing to do would be to just double the aluminum on the left and double the iron on the right. And then we have 2 and 2, 2 and 2, 3 and 3, and we're good. Now, some of the, I'm going to start right off. I'm going to go to the dot can because most of these are pretty straightforward. But we can't touch this. We can't. We have copper plus oxygen goes to copper to oxide. So, what you should look at. Typically, what we're going to see is we want to balance all non-oxygen atoms first, and then move to the oxygen atom. However, when we balance the oxygen, we have to double check and make sure we didn't screw up anything else. So we see there's one copper. See two oxygen on the left, one oxygen on the right. So what do we have to do? We have to double the oxygen. To do that, we have to double the copper oxide. When we double the copper oxide, now suddenly it's one copper, two copper. So, and you have to go back and double the copper on the left. So 2Cu, 2CuO. So we're not allowed to just say a half molecule of oxygen. I mean, technically you can, and in some definitions that would be okay. But we're going to try to keep it all integer values. Because if we look at this on the atomic level, you can't have half a molecule. I don't have one molecule, two molecules, three molecules of oxygen. Now this one is standard combustion. This one is what? Probably methanol plus oxygen goes to CO2 and water. Type of reaction we'll see a lot more in the coming minutes, coming day or so. Is that methanol, that when we burn a carbon hydrogen compound, it's going to produce CO2 and water. So I'm going to look at carbon first. I see there's one carbon on the left, one carbon on the right. I'm going to leave that. That's good. Next, I move to hydrogen. I'm going to do oxygen last. Why am I going to do oxygen last? Oxygen appears in two molecules, two compounds on the right. So if I try to balance oxygen and two compounds on the left, if I try to balance oxygen, it's going to get all messy. But hydrogen and carbon only appear in one compound apiece. So I see two hydrogens, let's say 4 hydrogens on the left, 2 hydrogens on the right, so I need to double the amount of hydrogen. So right now I have 1 CO2 and 2 waters. Now, so carbons and hydrogens are balanced. Oxygen, on the other hand, I have 3 oxygens on the left, and now 1, 2, 3, 4 on the right. It would be so easy to make it a half molecule of oxygen. I'd balance it. Well, actually, that'd be 1.5. I'd have to do 1.5 molecules of oxygen, 3 halves essentially on the left. However, once again, we need an integer value. So what do we have to do? If we leave that as 3 halves, we can get rid of the fraction by doubling everything. We double this, that goes from 1 to 2. 3 halves to 3. 1 to 2, 2 to 4. So now we have 2 carbons, 2 carbons. 8 hydrogens, 8 hydrogens. 2 plus 6, 8 oxygens. 2 times 2 is 4. 4 plus 1 times 1 is 4. 4 plus 4 is 8. Everything is balanced. And all these combustion problems balance the carbon and hydrogen first. That was a hard one. Not all combustion problems will be so hard. Now here's one that's a tricky one. Iron 3 sulfate plus magnesium goes to magnesium sulfate and iron. One trick to this one, there's a lot of elements in here. One trick is if you see an oxyanion that is identical on both sides, you can leave it as one unit. You can balance it as, instead of 2 S's and 2 S's and instead of 2 S's and 8 oxygens, you can make this. You can make this 2 SO4s. Make this 2 SO4s. And so I'm going to bounce the iron. And if I have to triple that up, I'm going to triple that there. Since there's 2 SO4s, I'm going to just double the MgSO4. Because I doubled the Mg, I have to double that Mg. So I'm going to just leave the SO4 together. SO4 together, and there we go. Now, one of the parts of this chapter will be recognizing the activity patterns. You can see something going on, you can kind of predict what the results should be. And there are certain types of reaction types that you can see here that you're going to be a certain amount of repetition there. Now, some of these reaction types will fit into more than one category, as we'll see. But first thing we're going to be doing is trying to classify some basic reaction types. Now these ones on here are the 5 most basic ones, but we're going to then break it down into 3 other categories that we can further describe these with. Now, one of the basic ones is a combination type. A combination type is 2 elements or 2 compounds come together to form a new one. such as a generalized reaction A plus B goes to AB. Now, as I said, they could be two compounds, two elements. Zinc oxide plus carbon dioxide come together to form smithsonite, which is zinc carbonate. So the CO2 binds to the zinc oxide to make one molecule, one structure. But it could be as simple as two sodiums and one chlorine forms two sodium chlorides. So the sodium atoms and the chlorine molecules come together to form a new compound where they've combined together. It doesn't matter that there's two sodium chlorides, we're forming one generalized structure out of two things. Of course, the opposite of that is decomposition. Decomposition, one compound breaks down into two or more compounds or two or more elements. This could be something simple like hydrogen peroxide will naturally break down into water and oxygen. But it could be something like we did in the second lab, where potassium chlorate breaks down into potassium chloride and oxygen. That KClO3 breaks into KCl and 3 oxygens when we heat it. You could technically break apart smithsonite, the zinc carbonate, back to carbon dioxide and zinc oxide. All these can be undated. Now, these next two are a little different, but single displacement is one element exchanges places with a compound. So generalized reaction A plus BC goes to AC plus B. The C is the anion. The A and the B would be normally cations, it's like metals. So, for example, the thermite reaction. The aluminum and the iron swap places. So the aluminum switches with iron oxide to form aluminum oxide and solid iron. So we're just swapping places with one molecule, thus the single displacement. Now double displacement, both atoms swap places. So they both have an anion. The two compounds switch out. Silver nitrate, hydrochloric acid, form silver chloride and nitric acid. So the H and the silver swap places, but now they have a pair. And finally, combustion reaction. Combustion reaction is a special type of reaction where a compound reacts with oxygen to form an oxide of some sort. So carbon plus hydrogen, oxygen form carbon dioxide and hydrogen dioxide. Dihydrogen monoxide. Two types of oxides. But you could also have sulfur burns in the presence of oxygen to form sulfur dioxide. You could have like nitrogen burns in the presence of oxygen to form either dinitrogen monoxide or various different oxides. You can even have things like magnesium burns in the presence of oxygen to form magnesium oxide. It doesn't have to form a gas. It can form a solid. It's just metal something burns with oxygen to form a metal oxide of some kind. Now, to make these reactions go, all reactions require what's called a driving force. They need something to push it from left to right. If we don't have this driving force, the reaction's not going to happen, which is why you don't have crazy things like we can't put lead to gold. There is no driving force that will allow that to happen. You can't easily split water into hydrogen and oxygen. You can, it's possible, but you need large quantities of energy to make this happen. Now, in order to make these things happen, we have to see a change in energy. We have to go to a more stable state. this form could be a change in heat energy, which we'll call enthalpy, and we'll look at that a little bit later, or a change in randomness, which is entropy, which we'll look at next semester. All these things will be a driving force. If a molecule breaks down into more complicated situation, it can help make this go. If it breaks down and produces a lot of energy, it can make this thing go, because we're becoming more stable. Now, since this chapter is largely about aqueous reactions, some of these driving forces, there's 3 such driving forces we'll look at largely. One called a precipitation reaction, which is when a solid results from the mixing of 2 aqueous solutions. So a double displacement essentially forms a solid. You pour 2 liquids together and a solid crashes out, forcing this to go towards products. There's going to be acid-base neutralization, in which an acid, which is known as a proton donor, HCl, HBr, HNO3, mixes with a base, which is a proton acceptor, typically going to be some sort of hydroxide, and they'll form liquid water and a salt. Salt is just an aqueous compound between a metal and a nonmetal. So the best example would be HCl and NaOH go on to form water and sodium chloride, NaCl. The formation of water is the driving force that pushes this to completion. And finally, oxidation reduction reactions, often known as redox. In this case, electrons get transferred to form a lower energy product. So how do we know if electrons get transferred? Typically, we look at the possible oxidation states. This comes back to early on, we looked in like chapter 2 or 3. We look at how do we predict the oxidation states of metals and nonmetals. We had to look at the periodic table where those elements showed up and whether they're in a compound or not. So I'm going to jump back 1 slide real quick just to show you something. All these reactions with a little asterisk are also oxidation reduction reactions. Now, sodium as element is charged 0. Chlorine as an element is charged 0. But sodium and chloride together would be Na plus and Cl minus. Sodium has gone from 0 to plus, chlorine has gone from 0 to minus. They have changed charge states. Hydrogen peroxide is H plus O1 minus, goes to H2O, which is H plus O2 minus, and oxygen 0 minus. In this case, oxygen goes from 1 minus to 2 minus and 1 minus to 0. Oxygen is changing oxidation states. Potassium chloride, chlorine is going to be 7 plus, and it goes to 1 minus. Oxygen is 2 minus, and it goes to 0. And this one, aluminum is 0, and it goes to 3 plus. Iron is 3 plus, and it goes to 0. And any of these combustion reactions typically are also redox reactions. Now we're going to go to actually looking at some of these a little bit more. Since we're talking about aqueous solutions, we need to talk about how does a solute actually dissolve? What does it mean to be an aqueous solution? So we know solid, that little s. We know kind of what it means to be a liquid, that little l. We know what it comes to mean to be a gas. But what does it mean to be AQ, an aqueous solution? An aqueous solution is when something, typically a solid, but it doesn't have to be a solid. It could be a liquid, could be a gas, is dissolved in water. And when this happens, this is said to be soluble. Now, if something were to remain behind, this is said to be insoluble or not soluble. This dissolution process is often called solvation. The solvation is when the compound or the ion gets completely surrounded by water. The whole idea of why does it disappear when it goes into water? In our naked, it never fully disappears, it just becomes too small for our naked eye to see. When we see salt crystals, when we draw salt crystals into water or sugar crystals into water, even a sugar cube, we're seeing trillions of molecules. They're all put together, and the sheer density of these molecules and compounds makes them appear visible to the naked eye. They're so densely compacted that we can actually see them. Just the same way as if you compacted enough material in one area, maybe you could see that thing from outer space. You have a dense compaction of material. Well, when you get dissolved, what is essentially happening? The water, which is already clear and colorless as is surrounding each and every molecule. And it's pulling these molecules and these compounds away from each other. So instead of being densely compacted, they start to get more and more dispersed as the water molecules surround them and move them away from each other, move them throughout the solution. A solution is, remember, considered a homogeneous mixture, which is when the mixture is uniform essentially throughout. In order for that to happen, we have to uniformly spread these compounds out. So they get dissolved, they get separated, and they get pulled apart from each other. So they get smaller and smaller and smaller until there's just single molecules and single compounds surrounded by lots of water. And so they become essentially invisible to the naked eye. Now, this dissolution happens because there is a certain amount of opposite charges, and opposite charges attract. That within water, there is a partial negative charge on the oxygen. Remember when we talked about dipoles? When we talked about dipoles, we talked about that, okay, the electronegativity of oxygen is big, the electronegativity of hydrogen is small, so the net effect is that there is a dipole pulling the electrons towards the oxygen. So that oxygen has essentially more electrons than it should. It doesn't keep the electrons, but it gets an unfair share. So we say that oxygen has a partial negative, represented by a delta negative, a Greek letter delta, a D minus. Now, since those hydrogens see a temporary loss in electrons that they should normally have, they have a delta positive, a partial positive. These partial charges can then be attracted to various different things that get dissolved. Take, for example, sodium chloride. We said sodium chloride is a Na plus and Cl minus. Well, the Na plus can get surrounded by large amounts of O's, the O's within that water. So the water spins around so that the O is oriented towards the sodium and it pulls it away. The chloride, which is 1 minus, gets attracted to the hydrogens. The water orientates itself so all the hydrogens are pointed towards it. So we have the negative surrounded by a bunch of partial positives and the positive surrounded by a bunch of partial negatives. And that way we slowly but surely pull all these ions apart to the point where we can no longer see them. Now, when a non-ionic compound dissolves, a non-ionic compound will contain more of the partial charges. Now, they don't separate, but these partial charges will be pulled into solution as they get separated and surrounded by the water. Now, if a compound doesn't have any partial charges, typically it won't dissolve in water. Remember when we said things like carbon and hydrogen are non-polar? Well, carbon and hydrogens are typically found in oils. Oils don't typically dissolve in water because they don't have a partial charge. There is one major exception, and that's CO2. It's a gas, and that even though it's non-polar, it can very well dissolve in water because of certain reactions it does. Okay. Now, when we look at various different types of compounds, we can address them and how they dissolve in water. Now, if they fully split up into all the ions that are possible, what's going to happen is they will strongly conduct electricity. So there is a quick demo I'll try to show in lab, or there's probably a video, there's maybe a homework question about this. Essentially, when you form ions in solution, you conduct electricity. What you need for electrical conduction is a good deal of positive and negative charges for the electrons in the electricity to jump through. If you had pure deionized water, it would not conduct electricity at all. Water itself does not conduct electricity. It's the stuff that's dissolved in it that makes it conduct. So when we fully break apart, they're going to form what's called a strong electrolyte, because a strong electrolyte is relating to the number of ions that get formed. Now, if something dissolves but doesn't break apart, it would form no ions. If it forms no ions, it won't conduct electricity, and thus these guys are called non-electrolytes. So a strong electrolyte might be a salt, like sodium chloride. A non-electrolyte would be like sugar. Sugar will dissolve in water, but it doesn't break apart. It's very carbon and hydrogen heavy and very organic. Now here's the kind of tricky one. When a compound will partially dissociate into ions, it will only weakly conduct electricity. What that means is when it goes into water, it doesn't break down 100%, but maybe breaks down to a fraction of a percent. Like maybe 5% breakdown, 10% breakdown. Some examples like this would be like vinegar. Vinegar is what's called a weak acid, in that when it goes into water, it only weakly breaks apart into a small fraction. And so it still conducts electricity, but it doesn't conduct it very strongly. Those guys are going to be a little bit harder to recognize, but they are a good deal rarer. So strong electrolytes, most of these are soluble ionic compounds and strong acids and bases. Sodium chloride, strong base like potassium hydroxide, strong acid like H2SO4, sulfuric acid. Non-electrolytes are chiefly soluble molecular compounds like methanol, SO2, sulfur dioxide, nitrogen dioxide. These will dissolve, but they don't really break apart. Weak electrolytes have properties of both ionic and molecular compounds. Weak acids and bases, like this is acetic acid, which is vinegar. Ammonia also will do that. Ammonia is a weak base, but it's a little bit harder to point out. Now, we'll go ahead and go through some of this. Now, one of the things we're going to look at is precipitation reactions. This page right here is a whole lot of words and really dense. However, come test time, I'm going to have a chart for you. There's these rules you can follow to predict a precipitation reaction, but there's also a chart you can also use to do the same thing. So don't feel like you have to learn these rules. Some of them will be obvious and be hopefully easy to memorize, but some of these will be a little bit harder. Now, we're talking about electrolytes and things that dissolve. What makes a metal and a non-metal not dissolve? What makes a solid deform when I mix two aqueous solutions? And this is the basis of precipitation reactions. Now, if I mix two aqueous solutions together, if I don't have an acid base, a redox, or a precipitation, there is said to be no driving force, and thus no reaction. So what the acid base is pretty easy to tell. The oxidation reduction is a little trickier, but one of the hardest ones to see is predicting when a solid will form. Sure, when you mix two things together, it's pretty clear. If you mix two things together in the lab, it's pretty clear because you can literally look and see that solid. Going back to those who had lab 2, we mixed potassium chloride and potassium chlorate in water, and then we added silver. In one case, it maybe stayed clear or maybe faintly white. In one case, it formed strongly white. We formed a precipitate in that case, and that way we could tell whether our sample was closer to potassium chloride or potassium chlorate. So there are some rules that should determine whether a solid should form. Now, the first two rules are the most important. Everything else is nice to know, but we can look at a chart to get the same effect. But the first step we're doing when we're predicting a precipitation reaction is to first write the double displacement products. If I tell you this is a double displacement reaction between sodium hydroxide and iron chloride, so the first thing you're going to do is swap iron onto hydroxide and then sodium onto chloride. We balance that out, we write the products. Then we look at our rules on either of the products. Do either of the products form a solid? Now in this example, I've given you the states of the matter, and the answer is yes. But if I didn't give you the states of matter, how would you determine that? And that's where we get to these rules. So let me read through the rules and break them down. Rule 1 is the always soluble, never solid categories. Elements of group 1, so lithium, sodium, potassium, rubidium, cesium, francium, and of the compound ammonia, NH4. Anything mixed with those are always soluble. That doesn't mean we can't have them as solids. It just means the second we add them to water, they will dissolve. They will dissolve in large quantities. Sodium chloride will dissolve in large quantities. Now, if I add enough sodium chloride, eventually it will precipitate. If I add enough, it is possible to have a saturated solution. However, this is soluble in large quantities. We take tens and hundreds of grams to saturate a solution of sodium chloride. All these precipitation reactions, we couldn't even get 1 gram to dissolve in a liter on most of the cases. We couldn't get 1 gram of the solid dissolve in a liter, and that is a lot. So anything with group 1 or ammonia is always soluble. So right there, sodium chloride, sodium is group 1. So by definition, that one is soluble. So that's going to be aqueous. Now, rule 2, nitrate, chlorate, perchlorate, and acetate are always soluble. Remember in the lab, we dissolved potassium chlorate and mixed it with silver, and we should have seen not a whole lot of solid. Why? Because chlorate is soluble in all solutions. Rule 3, here we get into the insolubility. Chloride, bromide, and iodide are soluble except when we mix them with silver or lead or mercury. Now, in the lab, we mixed potassium chloride with silver nitrate. Silver nitrate, the silver mixed with the chloride to form that white solid that we saw. Because chloride is soluble except with silver. Now, 4 and 5 and 6, we start to get to the less soluble compounds. Except for rule 1, carbonates, sulfites, phosphates, and chromates are insoluble. The carbonate is not soluble except when you mix it with, say, sodium carbonate or potassium carbonate. With the exception of rule 1 and barium, hydroxides and sulfides are insoluble. So sodium hydroxide is soluble, but barium hydroxide is soluble, but say iron hydroxide is not. Because iron hydroxide doesn't fall under rule 1 or barium, iron hydroxide would be a solid. Iron hydroxide would be a solid. Then with the exception of guideline 2, nitrates, perchlorates, acetates, silver, mercury, and lead are always insoluble. So silver really doesn't like to dissolve in things. Mercury really doesn't like to dissolve in things. Lead really doesn't like to dissolve in things. Except when, say, silver nitrate or silver perchlorate. And then, finally, with the exception of compound calcium, strontium, barium, and ions from rule 6, all sulfates are soluble. So sulfate is almost always soluble except for calcium, strontium, barium, silver, mercury, and lead. So these rules guide whether a solid should form. Solid should form. Where we're going to take these guys is we're going to we'll go ahead and finish after this slide. Where we're going to take this is we're going to start writing these reactions and trying to predict whether a solid will form. Eventually, we'll go to writing what's called a net ionic equation, where we show only the driving force, only what is actually happening. So, aqueous compounds, when they get dissolved in water, you're going to either have electrolytes or non-electrolytes, depending on whether ionic or molecular. Any ionic compound can be separated into cations and anions. Now, this is only true for strong electrolytes, aqueous. Solids, liquids, gases do not get split up. Solids, liquids, gases do not get split up because when they dissolve, if they're not dissolved, they are a whole compound. But when I say lead nitrate in solution, what that means is I have lead 2 plus floating around and NO3 1 floating around. The aqueous, remember when we talked about solvation, the aqueous meant each of these ions are surrounded by water and floating around like like rafters on a lazy river. They're maybe bumping around into each other, but for the large part, they're just floating on their own. We write them together out of convenience, but really they're floating by themselves. If they form a solid, suddenly they've stuck together. They're like, they have a double tube there. They're not separating, they're not splitting apart. Please note that nitrate is left as one anionic unit. Nitrate NO3 1- is an oxyanion. If you were to split this apart, you don't break it apart into N's and O's. Nitrate is one anion. Nitrate is one anion. And the subscript becomes the coefficient. So we will get to on Wednesday learning how to write these guys as an ionic equation. Today we've been talking about writing the overall equation, which is standard method. Everything's uncharged. We're going to write it as they are. But we're going to get to ionic equations where we split down the aqueous to the charged ion units. And that's where we're going to go. But that's where I'm going to stop for today. I was going to say I will start tomorrow by pulling up, showing the chart that I will provide for you for the test, so you can see what that is and kind of how to read that. The chart is so much easier to use than, say, those rules, but you have to know how to read the chart. You have to be able to use that in order to be able to use that to the fullest. So, okay, I will talk to you a little bit later. Have a good day.